6.3 is on square roots, square root functions, and inequalities. Now, a square root function obviously is just a function with a square root in it. And so the parent function of a square root function is just f of x equals the square root of x, and that's it. So square root of x is your parent function. If I wanted to graph this parent function and I use a table, I cannot put any number in under a square root that makes that under square root negative, because you cannot take a square root of a negative unless it being imaginary. So for this to be a real number, we have to put in 0 or greater in for this x. So when we start graphing this, I'm going to put in 0 in for x because that's the lowest number I can put in. Put 0 in, I take the square root of 0, I get 0. That is our starting point for this graph. The starting point basically is kind of like the end point of a graph. It doesn't go on forever in one direction. If I put in numbers, any numbers I want in for x, I could put in 1. Square root of 1 is 1, so it goes up 1 over 1 up 1, just like any other parent function that we talk about. I could put in 2, I could put in 3, but I'm going to put in 4 because the square root of 4 is 2. That gives me a very nice number or point to graph. So 1, 2, 3, 4, 1, 2, there's another point. If I put in 9, I get 3. So if I put in 9, I get 3. So basically this graph is going to look just like this. And it's going to go on forever because I can put in any x value greater than 0 I want. And it's going to go on forever. Okay, so with that said, with all of that said, let's talk about the domain of this function. The domain of this function obviously starts at 0 because we cannot put a number in underneath or less than 0. So x is greater than or equal to 0. If you wanted to do interval notation, we would say 0 to infinity. That's another way of writing it, of course. Now, the range, the y values. If you look at the y values start at 0 and go up. As you can see on the table, 0, 1, 2, 3. We could have decimals in there. So y also starts at 0 and goes up. So y is greater than or equal to 0. Or again, you could say 0 to infinity. The intercepts of this graph. In this case, the intercepts, of course, the x-intercept is where it crosses the x-axis, and that's 0. The y-intercept is also where it crosses the x-axis, and that's 0. So the intercepts are x equals 0 and y equals 0. What is not defined? Well, it's not defined if x is less than 0. So anywhere x is less than 0, it is not defined. The end behavior. As x approaches 0, y also approaches 0. As x approaches infinity, y also approaches positive infinity. So that is the end behavior. Because you have an end point, you're going to write the end behavior a little bit differently than you normally would. Okay, so let's go on to example 1, and let's talk about domain and range. When you look at a function, f of x equals the square root of x minus 3, you cannot have a negative value underneath the square root sign. So in other words, with your domain, x minus 3 has to be greater than or equal to 0. So this has to be greater than or equal to 0. So if I solve for it, x has to be greater than or equal to 3. So that is my domain. X has to be greater than or equal to 3, otherwise whatever's underneath the radical sign will be negative. The range. Now, if I did put in 3 in for x, I'll get 0. And because it's just like the parent function at that point, it's going to go up from there. So in this case, y is greater than or equal to 0. Now that's not always the case, but in this case it is. Now the reason that's not always the case is because what if you're adding something beyond the square root? Well, the square root's going to be 0, but then you would add that. So here's example 1b. Example 1b, x has to be greater than or equal to -6 because that's the lowest number x can be. Otherwise, you're going to have a negative underneath the square root. When I put in -6, I get 0 here. However, y will be 2 then. So therefore, y is greater than or equal to 2. So I'm going to repeat what I just said. If I put the lowest number for x in, I can, -6, and I put it in here for x, I get 0 here. Well, the square root of 0 plus 2 is 2. So therefore, y has to be greater than or equal to 2. It's always greater than or equal to, or possibly less than or equal to this number here. All right, and that brings us to the transformations. We kind of already alluded to some of the transformations by just doing these couple examples. But A, remember, is the orientation or the shape of the graph. Now in the parent function, A is 1. Okay, what we just looked back here at the parent function, A is 1. Now, so that anytime A is 1, it's going to be the normal shape and orientation. So if A is greater than 1, it's a vertical stretch. And of course, it means it's going to go up higher, faster. If A is less than 1 but greater than 0, it is a vertical, or I should say vertical compression. Which is a flatter graph than what the parent function is. If A is negative, then the graph actually opens down instead of up. And that's called a reflection. And of course, that's in the x-axis. So remember the A value of our parent functions or our general form transformations is always the same, and it's no different here. Now, h, depending on what h is, it's what you're subtracting, that is going to be the shift in the graph. Just like we saw back here, where x, the parent function, had to shift to the right 3 because h is positive 3. We're subtracting h, so therefore x has to start at h. So h is the shift right when h is positive, shift left when h is negative, and of course the domain typically, of course, is to the right of h, because usually anything to the left of h is going to be negative underneath the radical sign. So domain typically is x is greater than or equal to h. Okay, so the domain is typically this. Now k is the vertical shift of the graph. Just like back here, y didn't move. It still started at 0 because k is 0. But when k moved to 2, all of a sudden y had to be greater than or equal to 2. So k is the vertical shift up when k is greater than 0, and it's of course shift down when k is less than 0. So if you're adding something that's positive here, you're going to move up on the parent function. If it's negative, like a minus, you're going to move down. Okay? So hopefully that makes sense. All right, let's move to the last parts here of the graphing of an example 2. So here I have a is equal to 2. H is actually negative 2 because it's the opposite of this. It's what makes, you put in for x that makes this 0. Okay, so to graph this, if I'm going to actually use transformations, I'm going to go ahead and use the fact that a is 2 and h is negative 2. Now k, of course, is 0. So my starting point is going to always be at hk. So it's going to start at negative 2, 0. Now, just like the parent function, we went over 1, up 1. But a multiplies the y value by that amount. So instead of going over 1, up 1, I am going to go over 1, up 2. Because a doubles the y value. Over 2 up 4 is our parent function. Or excuse me, over 4 up 2 is our parent function, but we're going to double it. So it's over 4 up 4. Over 9, 2, 4, 6, 8, 9. Over 9 up 3, but we're going to go over 9 up 6. And it's going to look like this. Okay, so graphing using transformations is very simple if you understand the transformations. You can always make a table, make a graph that way, but this tends to be quicker. All right, so here my h is 5, positive 5. My k is positive 3. So just like I said before, that our starting point is going to be 5, 3, because that is our HK. 1, 2, 3, 4, 5, 1, 2, 3. So our starting point is there. Now we're going to use our vertical compression, 1/4. So instead of going over 1, up 1, we're going to go over 1, up 1/4 as much. Over 4, up 2, we're going to go over 4, up 1/2. So it's a very flat line because of the 1/4 for your a value. Now the domain and the range, the domain starts at 5 and goes to the right, so it's going to be anything x is greater than or equal to 5. The range starts at 3 and goes up, so it's anything greater than or equal to 3. All right, let's move on to example 3 in the book. F equals 200 square root of t. F is the number of frequencies per second. T is the tension in pounds. So obviously, if the tension goes up, the number of vibrations will also go up. They would like us to graph when t is between 0 and 10. So if we make a table between 0 and 10, we could do a number of things. We could type in 1, we could type in 2, 3, 4, 5, 6, 7, 8, 9, 10. Now you might need to use a calculator for some of this, but you might not have to use a calculator for all of it. If I put in 0, there's 0 tension. Obviously, there's going to be 0 vibrations. If I put in 1 pound of tension, it's 200 vibrations because square root of 1 is 1 times 200. 4 is the square root of 4 is 2. 2 times 200 is 400 vibrations. Oops, I wrote that under 3. Sorry about that. And 9 would be 600 vibrations. If I put in 10, you would have to probably figure out what 10, the square root of 10 is. I know it's going to be 3 point something. Let's go ahead and do that. So I take the square root of 10, and I get 3.162277766, but I multiply that times 200, and I get 632.5. So that should be enough